Hello and welcome to this video. In this video we're going to start looking at the practicals that you'll need for the AS section. So we're going to do it in the order that they're given on the AQA website. So we're going to start with the waves practical of forming a stationary wave, and we're going to investigate the relationship between the frequency of the wave that we see and the length of the string that we're actually having. What I will say, the tension that we're going to put across the string is what we're going to do in this case. But when I go through these practicals, I am choosing a very specific method that I believe is the best method to do. When you do it in schools, your teachers, or if you're at a different tuition center or lab or wherever you're doing these practicals, different people will give you different instructions on how to do these practicals. Now, while my way is one way that you can do these practicals, it's not the only way that you can do these practicals. Different things will be investigated differently. So in this case, we're going to investigate how the tension affects the frequency. In another video or in another experiment, you might investigate how the length affects the frequency, and so on, right? So while all of these videos will go through a method of doing it, it's never the only method of doing it. Okay, so let's get started on this setup then. So in order to make a stationary wave and investigate a relationship, we first have to have some idea of the equation for stationary waves. And now, if you remember from waves, we have the frequency of a stationary wave on the first harmonic is equal to 1 over 2L times the square root of T over mu. Okay, now this is the equation we're going to be working with. This is the basis of everything. As soon as we know what equation we're working with, we are investigating the relationship between F and T. Okay, that means in order to investigate how F is affected by changing T, we have to know what the length of the string is, and we have to know what this mass per unit length is. So these are preliminary measurements that we have to make before we start doing the experiment in order to make sure that we have constant values. Now, in order to measure mu, okay, so first thing we need to do is measure mu. Mu is the mass per unit length, if you remember. So that means that we need to know the total mass of the string, or in most cases it will be a wire that you're using. You need to know the total mass of the wire, and you need to know the total length of the wire. Now, the mass of the wire you can easily measure with scales, and the length of the wire you can easily measure with a ruler. Okay, it will probably be a meter ruler because you're probably going to want a large wire. In some cases, your teacher might give you a piece of wire that is specifically designed to be some length. But now you're making measurements, you have to also think about the uncertainty on these measurements. So let's just put as an aside, the uncertainty of these measurements when we're using this equipment is going to be half of the resolution of the equipment that you're using. For example, if your scales read to the nearest 2 decimal places. So if, say, you, for example, got a scales reading of 2.56 grams, your uncertainty is you don't know if this was rounded up or rounded down. So it means you have plus or minus. So your actual value with your uncertainty is you have 2.560 plus or minus 0.005, where your resolution in this case is it reads to the nearest 0.01. So half of that is 0.05, and this is actually your value for the mass. Now, we'll worry about these uncertainties later, but for now, just make sure when you take the reading, also make a note of any uncertainties that you have, because they will be very important when it comes to your end result, especially for practicals where you know the result you're expecting to get, and it will make your life much easier. The same thing will happen for the length with a ruler. A ruler can measure to the nearest millimeter, so your uncertainty is ½ millimeter. Okay, now let me get rid of this. So when we measure the mass of the wire, we're measuring the mass of the total wire because we want to make big measurements so that we reduce our percentage uncertainty. So we get the whole wire, literally just wrap it up into a coil or something like that, and then place it on the scales and read your mass. For length, you want to then stretch it out and then measure the length of the ruler, making sure both times you're noting your uncertainty, and then you can calculate your value for mu. That's fairly straightforward. Then you can then set up the actual apparatus. Now the actual apparatus is going to look something like this. So you will have a vibration inducer. I believe that's a technical term, I'm not actually entirely sure. But these vibrational inducers will work in different ways. Some of them you will want to attach straight to the inducer. Some of them you want to thread through a hole on the inducer. I'm going to take the example where you'd be threading through the inducer. So effectively, actually no, I'll take the example where you just have to attach the thread to the top of the inducer. So your inducer will have some body to it, and then you'll have some metal pole here where you'll attach the wire on the top by tying a bow around it or something like that, as long as it's attached. And this is on the table, and at the end of the table you're going to have a pulley. Now this is ideal, an ideal pulley. Obviously in the case of a practical, it has some uncertainty, but we're going to ignore that for now. Then this is going to go over the pulley and come down. And in order to create tension in the wire, we have to hook on some mass to the bottom. And this mass, M, is a known mass. Okay, so this mass must be known. Okay, now to actually figure out what the harmonic should be, we have a mass, we have a length L, and the length L is actually going to be from this point here to the very part where the wire touches the pulley, because that is where you have two nodes and we're trying to form the first harmonic in this case. So this is your length L. Okay, now we know L, and we've, in your practical logbook, you'll have written down L, and you know mu, and you'll have written that down. Both of them will have some uncertainty, and we'll deal with that later. Now we want to investigate how increasing the tension or increasing the mass that we're putting here is going to affect the frequency required by this frequency vibration inducer to form the first harmonic. Now we know the first harmonic is going to look something like this, right? We want it to constantly go up and down almost so quickly that it just looks like we have a top and a bottom and we have no in between. Now in order to do that, you need to make a few measurements. So what you're going to have is you will have the frequency that you have. Actually, let me put this in a table for now. So let's have a table where you need to measure the mass, and we're going to put it in kilograms straight away, of what you're putting on the end here. You can then convert that into tension just by multiplying it by G, because the tension in the string coming up here is going to be the same as mg. So you now have the tension in the wire, and then what you're going to work out is the frequency, but you're going to do 3 tries of the frequency, and then you're going to take an average of those. Okay, so this means what you're doing is for each different mass that you place on here, you will then keep the length constant. You obviously can't change the mass per unit length of the string because that's a property of the string. And for each different mass, you record the tension in the string, and then you will change, so there will be a dial on this inducer, and you change the frequency until you can see the first harmonic. Then change the frequency again, and then try and change it back until you see the first harmonic again. You'll get 3 different results. You take an average, you then change the mass and carry on, and so forth. Okay, and all of these should be in terms of hertz. I don't have space here, but these will all be in terms of hertz because they are frequencies. Okay, Now, if our whole goal is to investigate the relationship between f and t, we know from this equation, if L and mu are constants, that means that f is directly proportional to the square root of t. Now, in order to prove this, we can plot two things. We can either plot f against root t, or we can plot f squared against t. It's entirely up to you which one you actually want to plot. Both of them will give you the similar looking graph. You'll just have different values on one or the other. But the whole idea of plotting these is just to show that they are directly proportional. So if I scroll down a bit to here, given that you know the mass, the tension, and the frequency, it's up to you whether you want to make an extra column for the square root of the tension or an extra column for f squared. In this case, I'm going to do an extra column for f squared, but you'll find that it will be identical to if you did an extra column for the square root of t. Now, the reason I've done this is I'm assuming this equation is right. Okay, this is the assumption I'm making in order to design this experiment. The whole point of what I'm doing now is to verify that this experiment that this equation is correct, and these two are directly proportional to each other. That means if I plot a graph of the, let's go with f squared up here and the tension across here, what I'm expecting is a straight line, because they should be directly proportional to each other. And then what you should also find is that if I take the gradient of this line as an extra check, the gradient should be equal, if we take this equation back, I have f is 1 over 2l square root of t over mu. But if I've squared the f, that means it actually becomes f squared is equal to 1 over 4l squared t over mu, which means the constant, the gradient, should actually be equal to 1 over 4l squared mu. And this is another check that you can do, okay? Now, this probably isn't necessary. As soon as you see a straight line graph, you're basically in the clear. You know it's directly proportional. But if you wanted to go the extra mile and then prove this is fact, and the whole equation works, not just the relationship between f and t, you can then see if this is correct. And if it is, then you're fine. And if it's not, then you have some error somewhere. Okay, so this is the outline of this experiment. In order to then come up with a conclusion, what you want to write about is the fact that if you observe this kind of straight line, then you see that you can basically conclude that the equation is correct and that f is directly proportional to root t. If you observe a curved line, you can talk about that still. The whole point of these practicals is not so to get the right answer. An experiment is just an investigation. If you find that you don't get a completely straight line, there's some reason for that, okay? I'm not saying that you've proven physics wrong, but there's some reason in your experiment that you've got that result, and that gives you a chance to try and explain that. You don't have to get the right answer with these experiments. What we're looking for is just that you have the effective skills in order to take data and then be able to analyze the data to make sure that everything makes sense. Okay, from this point, I'm just going to recap very quickly how you would do errors on this. So in order for all of the values, you might remember from the uncertainty video that if you want to, everything in this equation is multiplied or divided, and when we multiply or divide, we always add the percentage uncertainty on every measurement, okay? We do have a square here, so you'll obviously get an uncertainty on each of these measurements, and when you square it, you're just going to times the uncertainty by a half, because you now have, sorry, you're going to times the uncertainty by 2, because you've now taken the same uncertainty and you've multiplied them together. So if this is right, I'm taking the uncertainty on the same thing times by the uncertainty on the same thing, so I have to add the two uncertainties. If I'm adding the same thing twice, it's the same as timesing it by 2. Okay, so this is how you're going to calculate your percentage uncertainty, and you'll end up with an uncertainty on this gradient too. And so in order to do that, you need to take your best gradient. So you need to add error bars. So based on whatever values you get for f or f squared, you'll have error bars, which you can plot something like this, which means this is the value that you got, but it could be anywhere in this range. And this allows you then to be able to make a really bad gradient and then a really good gradient. And then you can take the difference between those and divide them by the best gradient, and you'll get your percentage uncertainty on the gradient. Okay. The most important part, like I say, is not to get the right answer, but to make sure that you're doing the method correctly and that you can analyze the results. And even if you end up with an answer that's completely wrong, you need to be able to explain the answer and try and come up with some sort of theory to why that happened. Okay, so this is how you're going to conduct the stationary waves practical. Thank you for watching.